Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structures class. And today I'm going to talk about the damped free vibration response of single degree freedom system under damped systems, as we have discussed last class. But today I'm going to focus on the decay of motion and take some examples on it. So let's go and know more about the decay of motion under the underdamped system. Okay, last time we have explained about the equation of motion that is going to be used in our underdamped systems, and we mentioned that the general solution is going to be, as you can see here, u of t equal to e to the power minus psi omega t times rho, which is the amplitude of motion, times cosine omega d t minus theta. And we designated this equation with equation number 4. Okay, so today we are going to look deeper into this. Okay, and we are going to look deeper into the curve that is going to envelope the motion, which we call it the envelope of motion. So now let's highlight here this envelope. So we are having something like this, for example, here. And let's have something like this here. This is the envelope that we are expecting here. The amplitude of motion in the beginning of the motion is u of I, for example. And this amplitude, as you can see, when the time goes by, you're going to find that this amplitude is decreasing. It is decreasing, right? Okay. Based on this, we are going to derive some equation that is going to bring or to make it easy for us to predict what is this reduction in the amplitude will be after certain number of cycles. Okay. So starting from the equation number 4 that we already have derived last time, this equation, okay, the envelope curves here, this one and this one, let's use the red color here. So we said that they are enveloped by rho e to minus psi omega t, and this is the minus form of it, e to minus psi omega t. So this is the envelope that we are having here, that enveloping our amplitudes. Okay. From this equation, from equation 4, the crest, so we can say that the crest, which means that the maximum amplitude, if we go back here, this is the crest here, which is the maximum of the displacement, whether in the positive or in the negative sides. Okay, so this is the crest. So the envelope that we are, this crest, or at the crest, the envelope is going to be used. The envelope curve equation applies. This means that our u of t, our equation, is going to be plus or minus, we said positive or negative, plus or minus, because we have two curves, okay, the plus or minus, okay, times rho, which is the amplitude, times e to minus psi omega t. This is our equation, okay. And if you look to equation 4, cosine, this cosine something here, it is, and the envelope, it is going to be inside this parenthesis, it's going to be 0, means that cosine 0 is going to be 1. Okay, so our equation is going to be u of t plus or minus rho times e to the power minus psi omega t, and there is cosine omega dt minus theta, it is going to be 1 by default. Okay, so let's go now at t, at time ti, any point ti. Our equation of motion, u of ti, or at ti, is going to be rho e to minus psi omega t I, right? Okay, and if we are going to have another time, another point that we want to get the amplitude at, or the crest at, let's assume that it is going to be at Ti plus Td, which is going to be the damped period. If you go here, because we are in damped system, so we are having the distance here from this crest to this crest is going to be our Td, right? So the distance from here to here, it is going to be Td, which is going to equal 2 pi over omega d. So half of it is going to be pi over omega d, and the other half is going to be pi over omega d. Okay, so based on this, we are going to have our equation of motion, which is the u of t I plus td. It is going to be rho e2 minus psi omega. Instead of ti, it is going to be ti plus 2 pi over omega d, which is going to be after a complete cycle, right? Here we are talking about the point, we're talking about point here, and then we're going to talk about this point, which is on the curve here and here, the crests. Okay. After that, we are going to have the relation between the two. I mean, the relation between these two. Okay, we're going to say that u of ti over u of ti plus td. Okay, or 2 pi, let's put it like 2 pi over omega d. We want to know what is the relation here between the two, right? We are going to make this relation, which is the numerator is going to be rho e2 minus psi omega ti, and the denominator is going to be rho e to the power minus psi omega ti plus 2 pi omega. So we know each one of the numerator and denominator is going to be here. Okay, if the output of this is going to be e raised to minus psi omega ti minus psi omega times ti plus 2 pi over omega d, right? This is what we are going to have here, and close this parenthesis. Okay, if you are going to rearrange this, you're going to find it equals to e raised to psi omega ti, psi, let's erase this part here. It is going to equal psi omega 2 pi over omega d, right? This is what we are going to end up with, okay? 2 pi over omega d. So this is the ratio between the u of ti and u of ti plus 2 pi over omega d. Okay. In this case, we are going to assume that this is an exponential function. So we have, like we said, that we have like u at point I, let's assume it's I here, over u of point I plus 1 cycle, means that 1 cycle here. 1 means that it is the next plus 1 cycle from here to here. So this is like u1, this is going to be u1 plus 1, which is u2, and so on and so forth. So we are going to have it as ui over ui plus 1 here, similar to this fraction here. So it is going to equal for us this relation that we have here, which is e psi omega 2 pi over omega d. Then we're going to say, let's take ln of the two sides here. So we're going to take ln of this. Let's have it with another color. So we're going to have ln here, and we're going to have ln here, which is the natural logarithm of both sides. Based on that, we are going to find that ln ui over ui plus 1, the ratio between the displacement at point I over the displacement at point I plus 1, which is one cycle after, is going to equal 2 pi psi omega over omega d. Right? This is what we are going to have here. This is what we are going to call it, something that is very unique. We're going to call it sigma. Okay, let's assume it sigma. And this sigma, we're going to give it this name, the logarithmic decrement. The logarithmic decrement. The decrement. What is the meaning of this? It is the decrement. It is a kind of decrement between ui and ui plus 1. Okay, this decrement is logarithmic in nature. So we are going to give this designation, which is sigma, logarithmic decrement. And then we are going to like reduce this in a way that we know it will. So we're going to put it like 2 pi psi, and this omega over omega d, is it okay if I put it like 1 over the square root of 1 minus psi squared? Is it okay? I think it's okay. From the previous video, you are going to find that this is okay because this is the ratio between omega and omega d. Okay? So here we want to highlight something, which is that this value, which is 1, the denominator here, this denominator is going to be almost 1, right? So it is going to be this denominator, as we said, the square root of 1 minus psi squared. Almost it is going to be 1, where for low values of damping ratios. Okay, so it is going to be 1 for our case. Well, what should we do in this case? Okay, we're going to arrange again our point. Okay, let's start from here. So we are going to say that our logarithmic scale is going to be equal to pi psi, which equals to ln u of ti over u of ti plus td. Okay, this is the same as we said. It is going to be equal the same as I said before, ui plus 1. It is the same, only we put this designation because we are going to use it later in a while. Okay, so based on that, if you look to this equation, we can say that e raised to sigma to the logarithmic decrement is going to equal ui over ui plus 1, right? That's what we have already said before. And based on this, if we have like 4 several cycles, I mean that our system is going to have something like this, several cycles. So we have like 1, 2, 3, 4, and so on. We have different cycles. So we have like n cycles. In this case, we are going to say that this ui over u, or let's assume it u1 here. Okay, let's erase this part. Okay, so we can say that the first amplitude, which is u1 here, this is u1, to the last amplitude, or at after n cycles, the amplitude, which is going to be u1 plus n, 1 plus n, is going to equal e to n sigma, right? Because we have n cycles, so this means that the decrement is going to be multiplied by one another. So e times e to the power sigma times e to the power sigma times e to the power sigma n times, right? So we are going to have this equation here, okay? The decrement that we are having is going to be exponential, and we can obtain the ratio between one point and the other. If we go back here, here, that's the point. We want to get the ratio between this amplitude and this amplitude, or the first amplitude and the last amplitude. So our equation now can give us this ability, okay, where this sigma equal to, as we said, 2 pi psi, okay? This is our sigma, okay? And we found something that is very interesting, that this is going to work for the displacement or acceleration. What is the meaning of this? That if we have a relation between t and u of t, we found that it will work for t and u double dot of t, means the acceleration. So our equation is going to work for both, okay? It is going to work for both. This means that instead of u1, we can use u double dot. So we can put it like this in a general form. We can put it like this: ln u1 over u1 plus n equal to n times sigma equals to n to pi psi, okay? This is going to be for displacement. This is for displacement. And then we can repeat the same, exactly the same ln, but we're going to say u1 double dot over u double dot 1 plus n equal to n to pi psi. The same also. Okay, this is going to be for acceleration, if we're going to talk about the acceleration. So why we enter the acceleration here? What is the reason for putting the acceleration? The point is, commonly acceleration is easier, okay, to be measured. Okay, it is easier to be measured compared to the displacement, okay, as we are going to see later. Okay, sometimes we are interested in what we call it the number of cycles required to reduce the amplitude to 50%. What does it mean? If we have a line and we have a lot of cycles like this, it goes like this. This is t and this is u of t, okay? Then sometimes we are interested in that we know this amplitude, how much is it, okay? So this is like u1, but we want to say after how many cycles this u1 is going to reach half, for example, okay, which is going to be half u1. We want to get the number of cycles. We do not know where exactly this cycle here, this crest or this one. We do not know. So to get the number of cycles required to reduce the amplitude to 50%, we can put it like small title here, to get the number of cycles, the number of cycles required to reduce the amplitude to 50% if we want to reduce our amplitude to 50%, how many cycles that we want to get? So actually the equation is going to be easy for us. We're going to say that 2 over 1, right? Remember that we want half. We're going to say that like this. 2, which is this, u1 over u1 plus n. So it is going to be 2 over 1 because we want it to be half. Okay, we are searching for the half. So it is going to equal e raised to the n sigma, right? The number of cycles times sigma. Or we can put it like ln, take ln for the both sides, ln 2, which is 2 over 1, which is 2, equal to n times 2 pi psi. Remember this? It is here, this is n and e, and then the sigma here is going to be 2 pi psi. Remember that we have said that before. 2 pi psi, which is sigma, which is the logarithmic decrement. Okay, so based on this, what is the ln of 2? Here we can say this ln of 2, it equals to almost 0.69, and it equals to 2 pi, which is a constant here, n psi. So we can make a relation between the two. We can make a relation between the two. As you can see here, if you look here, like we have like n and we have psi, and we can say that this is a constant and this is another constant. So we can draw a relation between the two. We can draw a relation between the two. Actually, for our case, if we go here and we can find there is a good relation that we can have here, which is related to or relating the damping ratio. Let's assume here damping ratio, okay, and the horizontal line against the logarithmic decrement, which is sigma, as I have explained here. If you take a look here, we are going to find that there is a relation here between the two. As you can see, this is the exact and approximate relations between logarithmic decrement and damping ratio. So we have the relation between the two. Remember that in the beginning in our derivation we said that this supposedly the logarithmic decrement equals to 2 pi psi, okay, over 1 minus psi squared under the radical. This is in the denominator, and we said that is going to be very small. And we said that for simplicity we're going to assume that our sigma is going to equal 2 pi psi. Okay, so if we are going to draw the relation between the damping ratio and the logarithmic decrement for both cases, you're going to find that here at almost like 0.2, look here, they are the same, exact, almost exact. So there is no difference at all if we are going to use the approximate equation that we have already derived before, or the accurate or the exact. We call this to be the exact, okay, the exact, and this is the approximate, okay, this is the approximate one. Remember in the derivation, in the derivation we were like telling, so sorry here, yes, in the derivation, yes, I remember here we said that, I think here, yes, here we said at this point, we said that 1 minus psi squared under the radical, we said that it is going to be almost 1. Actually there is some difference, but we say that it's almost 1. Now we can find that in our case we are having this relation is going to be almost the same for around 0.2. They are going to be almost the same. After that, starting maybe from 0.35 or so, they are going to be different here. So we are on the safe side, and we are right in our assumption to use the approximate is going to be accurate for us. Okay. Another thing which is relating the giving us the relation between the amplitude at the beginning and the amplitude after n cycles, that is going to be half of it. So as we said in the previous slide, we need to make a relation between the two, which is this equation. Here we said that there is an equation that we need to make between the n and the psi. So this equation is going to be like drawn between n and psi, and here this is the relation. So here we are going to find that the damping ratio on the horizontal line and J 50% means that the number of cycles, okay, required. So this is the number of cycles required to reduce the free vibration amplitude by 50%. Okay, remember that our equation that already we said that is going to be like 0.69 equal to 2 pi n psi. This means that almost n psi equals to 0.11, right? So this means that we are going to put, this is the number of cycle here, and this is the damping ratio, which is psi. So they are having this relation that n is going to equal 0.11 over psi. So if we are going to draw it here, you're going to find that this is the relation. This is the relation here with the thick line here. So this means that at 0.05, okay, at 0.05, we're going to find that the number of cycles required to reduce the amplitude by 50% is 2. And if the damping ratio is like 0.1, we're going to find that maybe after one cycle, the amplitude is going to be reduced to the half. But on the opposite side, if we are going to decrease the damping ratio, we're going to find that we need a large number of cycles in order to reduce the amplitude. Okay. Okay, so now this is what we call it the number of cycles. Okay, this is n here. We call it n or J50 according to the textbook, but they are the same. It is the number of cycles required to reduce the free vibration amplitude by 50. You understand this? Whenever that we start like this and we have the amplitude like this, okay, then the first amplitude is going to be reduced after one cycle to the half. If we have damping ratio equal to 0.1, 10%. Okay. However, that if we have less damping ratio, okay, we are going to find that many number of cycles here needed in order to obtain or to reach to the 50%. Okay, so this is going to this is the end of this part, which is related to the decay of motion. Let's go to the next part, which is related to the free vibration test. Okay, so we're going to talk about the free vibration tests. What are the free vibration tests in general? I'd like to read this part from the textbook. It is going to give us information about this. Because it is not possible to determine analytically the damping ratio for practical structures, that whenever that we have practical structures like real 3-story building, for example, how we are going to get its damping ratio, okay, or it is the damping ratio is going to be something difficult for us to measure here because it's a real one, okay. So what we are doing here is a way for us to help us for determining this experimentally, for example. Free vibration experiments provide one means of determining the damping. Okay, we call it free vibration experiments. Free vibration tests provide one means of determining the damping. Okay, such experiments on 2 one-story models led to the free vibration records presented in this figure that you're showing here, that I'm showing here. This is figure 114, we have like two different types of, this is an experiment. It was done in University of California, Berkeley, and we have like plexiglass and aluminum. So as you can see, this is maybe the glass or plexiglass model, and this is, it seems like a shaking table, and here we have like the aluminum like test model here. So we can, like, after shaking this models, we can obtain or we can determine the damping ratio for them. If we're talking about lightly damped system, because we need to be like similar to buildings, so it is for any building, it is, as we said, should be less than 0.2. So in this case, if we are going to make an experiment for the model and we put a test model on a shaking table, we can use our equations that we have done before. These are the two equations, okay, that we have already derived or explained before. So this is like the damping ratio equal to 1 over 2 pi. J here is putting J, but it is actually for us, it is N. So it is, as we said, it is the number of cycles that we are interested in, times ln ui, which is the amplitude at the beginning, over ui plus n, which is after n cycles. This is for the displacement. We're going to repeat it, as we said, if we are talking about acceleration. So it is going to be the same. So our damping ratio can be obtained if we have 2 pi n, okay, ln u double dot I over ui plus n. So we can measure, as I said, we can measure the acceleration easily. In these kind of tests, it is easy to test the acceleration. So we can apply the test and we can get the ratio between the acceleration after several n cycles, and then we can obtain the damping ratio of the system. Okay, so this is the reason for making free vibration tests of models. Okay, now if we are going to look deeper into this, you're going to find that we have, as I said, we have like plexiglass like model, and we have the aluminum model. Okay, let's erase here this part here. As you can see, for the plexiglass, which is going to be, this is the free vibration record of aluminum model, which is be here for aluminum model, which is this one, I guess. It is going to be here. This is the record of the acceleration. So again, we have, as I said, we have the shaking table here, and it is connected with wires and so on. So we can have data acquisition system, and we can measure what is the acceleration that is going to be imparted or going to be sensed by the system itself. So we are measuring the acceleration in terms of g, which is the ground acceleration, okay, and in the horizontal axis we are recording the time in seconds. So here, this one, it is related to the aluminum, this one is related to the plexiglass. Okay, can you imagine here? Can you think about this? Look to the decay of the case of the plexiglass, for example. Exponential decay is very high here. Look here, almost it is like linear, very small decay going there. There is a difference between the two. Okay, as I said, the first one, it's aluminum, and the second one is plexi, free vibration record for the plexi glass. Okay, this gives us the difference between systems and materials, which is going to affect the way of the system decay of motion, okay, or the motion decay, okay, as you can see here and here. Okay, take care, because we are going to use this one as one of the examples with the numbers. So for example, here we have like recorded the beginning. At the beginning of motion, it was u double dot was 0.9, almost 0.9 g, and t1 was almost 1.1 second. And after that, we found that after several cycles, we found that u double dot after 10 cycles, because this is u1 and here u11, after 10 cycles, the u double dot reduced to be 0.07 after like 3.84 or at 3.844 seconds. Okay, so this means that we are having decay of the motion, okay, within almost like 2.7 seconds. Okay, now let's go and see what next for us. Let's have an example that is going to help us to understand more about the decay and how to deal with it. Okay, the example is 2.5 in Chopra book, you can find it, and we are going to use the plexiglass model record that we have recorded already. As we said, it is a relation between the acceleration in terms of g, which is the gravitational acceleration, and the horizontal one is going to be time in seconds. Okay, as you can see, we have something here which is linked to the top of this plexiglass, and everything is recorded here. So determine, this is the example, determine the natural vibration period and damping ratio. So we need the natural vibration period and damping ratio of the plexiglass frame model. As you can see, this is in this figure here. So as I said, we are talking about this plexiglass here. From the acceleration record of its free vibration shown in this figure. This is, as I said, we can obtain it at the lab. We can have this relation between the time and the acceleration, okay, using a data acquisition system after being connected with the top of this plexiglass model. Okay, now let's go and see. The peak values of acceleration and the time instance they occur can be read from the free vibration. As you can see here, this is the first point. We have u double dot 1, which is u double dot 1, peak 1, it was 0.915 g. However, here after 10 cycles we found that, which is peak 11, it was 0.076. okay, the time here was 1.1, here the time was 3.8. I mean that after almost 2.7 seconds we reached from 0.9 to 0.07. Okay. Now we want to get what? Again, they want the natural vibration period and the damping ratio. Natural vibration period and the damping ratio. Okay. Now we have TD, we can obtain it easily, right? Because the difference between 1 and 11 is 10 cycles. And their time is 3.844 minus 1.1. So we have like 1, 2, 3, 4, 5, 6, 7, 10 until we reach to the 11 here. So we're going to subtract from 3.844, we're going to subtract 1.1. Then this is going to be exactly the difference in time. This is going to be the total time over the number of cycles. We have 10. So we have, this is the number of cycles. Okay, number of cycles. Already it is read for us. Okay, we know it. Okay, so from here we can get TD. We have TD. It is the damped period of the system, which is going to be 0.273 seconds. Okay, the second requirement that is needed is a damping ratio. From our equation, if you go back to what we have explained before, this is the damping ratio that we are using here. This is the damping ratio, 1 over 2 pi n ln u double dot I over ui double dot. Actually here this is double dot. Okay, I'm sorry for this. This is double dot. Okay, u double dot I plus n. Okay, in this case we are going to have the next part here, which is related to the second requirement in this equation, which is going to be 1 over 2 pi n, this is n in our case, ln, this is u double dot at 1, for example, and this is going to be u double dot at 1 plus 10, which is n in our case. Then we know this, and we know everything here. So the damping ratio is going to be 0.0396. Take care, it is read like this, and we put it like percentage, 3.96. This system is having 3.96 damping ratio. Okay, so now this is a very good example for us on how we can calculate the damping ratio and the damped period of a system based on experimental data in the lab or at the lab. Okay, now let's go to another example that is going to give us like another hints and let us understand more about how we can do it with real structures. So let's read. A free vibration test is conducted on an empty elevated, take care, it is empty, elevated water tank. So we have this water tank as you can see here, okay, and this empty elevated, it's empty, there is no water inside it, but it is an elevated tank as you can see, such as the one in this figure, okay, we're talking about this figure. A cable attached to the tank, take care, cable is attached to the tank, applies a lateral horizontal force of 16.4. The meaning, actually we are like having a cable, okay, attached to the tank, okay, and it applies like 16.4 kips, okay, lateral force, horizontal. So it is horizontal. We need to be careful here. So we applied like horizontal force using a cable as someone is like pulling it. Someone is pulling it. And the value of the force was 16.4 kips and pulls the tank horizontally by 2 inches. So it moves, okay, it moves. We measured this movement, okay, it moves like 2 inches, okay. Okay. The cable is suddenly cut. So this cable is suddenly cut, okay? And the resulting force, free vibration is recorded. So we just pull it with a value, or the force was 16.4, and then suddenly we cut it, and then let this tank to like freely vibrate. And then we recorded this vibration. At the end of 4 complete cycles after n, okay, after n equal to 4, okay, the time is 2 seconds. So our time was 2, okay, and the amplitude is 1 inch, and the amplitude, which is u, let's assume the amplitude for our system, it was 1 inch, okay. Clear? I hope that everything is clear up till now. Okay, so we have this information after 4 cycles. The time was 2 seconds, and the amplitude was 1 inch. From these data, compute the following: the damping ratio, we want the damping ratio, natural period of undamped vibration, which is TD, stiffness, weight, damping coefficient, and number of cycles required for the displacement amplitude to decrease to 0.2 inches. Okay, so now let's go and understand how we can deal with this. Okay, first of all, let's start with the damping ratio. Okay, let's go and use the damping ratio. First of all, for the damping ratio, if you remember, we said that before, okay, that our damping ratio equals to 1, if we go back, 1 over 2 pi n times ln u double dot 1 over u double dot 1 plus I, okay, 1 plus n here. So here in our case, we are going to have damping ratio equal to 1 over 2 pi r, which is the number of cycles. Already we have it here. Ln the value of the amplitude over the value of the amplitude after n cycles. They said to us after n cycles, after 4 cycles, n, the amplitude was 1. So it was here 1. Okay. However, when we pulled it with 16.4, the number that, or the displacement was 2. So we have reduced from starting from something like this. It was 2 here, and we reached 1 here after 4 cycles. Okay, it is not right, but it is after 4 cycles. This means that we can apply easily in this equation, and everything is known for us. Then we can obtain the damping ratio of this system. This is a very good example for us in order to obtain the damping ratio of a system, of an existing structure. What we need is like a cable, as we said, to pull it and then record the displacement at the beginning of the motion and leave it to vibrate freely, and then record whatever that we can record in terms of the number of cycles and the t and u, the displacement. Okay, we are going to assume that this structure is having a small damping ratio because it is structure. Okay, so this means that we are going to assume small damping. Okay, this means that our TD, which is the second natural period of undamped, of the undamped system, or the undamped vibration, it is going to be TD, which is going to be like 2 over 4. Okay, so we have, this is TD equal to 2 over 4 because we have 2 seconds over 4 cycles, right? 2 seconds over 4 cycles. We started with 2, and then after 4 cycles, okay, after we have like 2 seconds, which is already recorded here from the beginning of the free vibration over 4 cycles. This means that our system is going to have like 1, okay, and then 2, and then 3, and then 4. Okay, so this is like 4 cycles. This was measured in 2 seconds, and we have 4 cycles. So TD is 2 over 4. So it's going to be 0.5. So what is the value of Tn, which is the natural period that they are having? We, as we have mentioned before, going to assume that Tn approximately equal to TD. Said that both of them, they are almost equal. Only difference 1 minus psi squared in the radical, right? Which is not going to make this big difference. So it is 0.5 second. Okay, so now we have A, B. Now we want the stiffness. What is the meaning of the stiffness? It is the force required for the system to, let me have a new page here. It's better to have a new page, I guess. So, yes, the next one, I think that we have a page. Okay. So the point is, in our system, if we have, this is the structure that we have, for example, or we have force, we have applied force here. Do you remember? We have applied force, which is 16.4 kips, right? And the motion of this structure, it was how much? It was 2 inches, right? So our stiffness is going to be, the force required to displace this structure a distance u that they have, or we have. Okay, from the beginning, in the beginning of this example, they said that we pulled it with 16.4 and we measured the displacement to be 2 inches. So we have here 16.4 over 2. It is going to give us 8.2 kips per inch. So what is the meaning of this? As we said, this is the stiffness of the system. What is the meaning of the stiffness? It is the force needed for displacing the mass of this system, which is an empty tank, by unit displacement. So we are having 8.2 kips are required in order to displace the mass or the empty tank by 1 inch. Okay, this is the meaning of the stiffness. Okay, the next requirement, it is they need the weight. Okay, weight, which is the weight here is going to equal m times g, right? If we go back here, they wanted the weight. Sorry for this. Yes, here we. Sorry. Yes, we are here. So they wanted the weight of the system. Okay, in our case, for the weight we are having, let's go here. Okay, for the weight, it equals to the mass times the gravitational acceleration, right? So we're going to say that our first of all, omega n, if you remember from previous lectures, we said that famous equation, it equals to k over m, right? So actually we are aware of k. Already we have obtained k in the previous, okay? This is k. And omega n, already we can obtain omega n easily, right? Omega n can be obtained easily. Omega n equal to 2 pi over Tn. Tn already we have obtained it, which is 0.5, right? So based on this, we can say that our mass is going to equal omega squared n over k. Omega squared n, we know that it equals to 2 pi over Tn squared, and k, it is known for us. Already we have obtained it before, okay, which is 8 point something, right? 8.2, for example. Take care of the units in every step that you are taking here. Okay, so based on that, we can say this omega n, it is going to be, after substitution, it is going to be 12.56, okay, and we are talking about omega n squared. This is squared here. Take care of this 12.56. It is in rad per second because this is omega, over 8.2, which is the stiffness that we have, which is in kips per inch. Take care of the units. So the final result here of the mass, we are talking about the mass, it is going to be 0.0519, and the units is going to be kips second squared per inch. Okay, that's what we are going to have, and based on this we can obtain the weight. Okay, so our weight now, okay, weight of the empty tank is going to be equal to the mass, as we said, 0.0519, which is, this is m, times the gravitational acceleration, which is 386, because we are talking about inch per second squared. This gives us value of the weight to be 20.03 kips. This is the weight that we are searching for. So what is the point, or what is the logic behind this? Whenever that we know the stiffness of, let's have this, if we know the stiffness of the structure and we know about its natural circular frequency, then it is very easy for us to obtain the weight of the system. Because as you can see here, weight in general is going to be function of what? Mass times the acceleration. So for us, if we know the stiffness and we know the natural circular frequency, then we can obtain the relation, because we have a relation between the mass, stiffness, and the natural frequency. Stiffness is known already, and we know how to obtain the natural circular frequency from the natural period of the structure. Then we can obtain the mass. Then this mass can be substituted in this equation to obtain the weight. Okay, that's the case. Okay, now let's go to the next point. The next point is the damping coefficient. So I think that they asking about the, they want the damping coefficient. Okay, they want the damping coefficient. The damping coefficient, as we said, is going to be related to the damping ratio and the critical damping coefficient. Do you remember when we said before that, do you remember this equation? Psi equal to C over CR, right? And we said before that CCR, okay, CCR, it equals to 2 omega m. Do you remember these two equations? Like, go back 2 videos and you're going to understand what I'm saying and what I'm talking about. So this CCR, let's use this, CCR in this case, going to equal 2 over omega, which is 2 times omega, which is omega n in this case. We are talking about the natural period. Okay. So in this case, 2 times omega, which is times m, which we can put it like k over omega. Is it okay? Because we have m here, right? So m and omega, then whenever we multiply them together, we are going to obtain k over omega. Remember it here. That's the relation that we have here, okay? Okay, so now this is 2 times k over omega. I think that we know everything in this equation, so we can put it easily. Can say that 2 times k, which is already 12.56, okay, times this 1 over omega, which is, yes, I think that there is, yes, I think that this is only for explanation, but we can put it from here directly. So let's like remove this and put it here. So it is going to be 2 times omega. Already we have obtained omega before, which is going to be 12.56, and here this is times m, which is already we have obtained it before, 0.0519, right? So this would give us, like at the end, 1.3, and the units for this critical damping coefficient is going to be like kip second per inch. Okay, so this is what we this is what we have here. Okay, this is what we have here. Okay, and after that we are going to look to this damping ratio. It equals to C over CR, right? So here it is going to equal C over 1.3. And the damping ratio, we know it. We know the damping ratio because already we have calculated before. It is going to be 0.0276, right? So from here we can obtain C, which is the damping coefficient, and it equals to 0.036. Okay, so it is, the unit is kip second per inch. Okay, so this is what we are searching for. We are searching for this one, which is the damping coefficient. The damping coefficient. Okay, the last thing here, I think we have another white page. The last thing it was, we are searching for, let me check here, the number of cycles required for the displacement amplitude to reach point 2. Okay, the point is we want, we want the amplitude U to reach 0.2 inch. Okay, we want it to reach 0.2 inch. So actually we started from 2 inches, right? We started from 2 inches and we want to go to 0.2 inch. So we want to know what is the number of cycles in order to get this value of 0.2. Then we're going to use our equation that we have already derived before. 1 over 2 pi n, which is the number of cycles, times L, the natural logarithm of ui over ui plus n. This is going to be the damping ratio already we have obtained, which is 0.0267 equals to 1 over 2 pi, it is known, n, it is our unknown here, ln 2 inches over 0.2 inches, right? It is before and after. This is the beginning and this is at the end. We want it from 2 inches to 0.2 inches. So it is only the unknown here. We can obtain it easily. Okay, so we're going to find that n after substitution is going to be like 13.28. We are talking about n as integer. It should be like 12 cycles or 13 cycles. So we're going to say that it is almost equal to 13 cycles. So after 13 cycles, we are going to find that our amplitude that we started after 13 cycles, it is going to reach 0.2. Okay, so this is regarding this equation and this requirement in the equation. Okay, now let's go to the last maybe example for us today. So we are going to talk about the example which is asking for the weight of the water required to fill the tank. In this example, which is our tank, it is 80 kips. I said before that this tank was empty, but we are going to fill it, okay, with water. The amount of water needed to fill it is 80 kips. Determine the natural vibration period and damping ratio of the structure with the tank full. So now water is going to be inside this tank, and we need to know what is its natural period Tn and what is its damping ratio. Tn and damping ratio. They are going to be affected by the mass. They are going to be affected by the mass. So we're going to start with the weight of the structure. First of all, the weight of the structure is 20.03, which is the empty tank, plus 80, which is the weight of the water. So this is the weight. Why we need the weight? In order to obtain the mass. The mass is going to equal the weight over the gravitational acceleration. This gives us this value. Okay. Now the next is Tn. What is Tn? We want Tn equal to 2 pi over the square root of the mass over k, right? This is the equation that we have obtained like 2-3 videos before. Okay. This means that our Tn equal to 2 pi over m, which is already given or already we have calculated, over k. K is already obtained from the previous slide. So we have everything known in this equation, and our t is going to be 1.12 seconds. Let's go back and see what was the value of this natural period in the previous example. Remember that Tn, do you remember? Tn was almost like approximately 0.5 seconds, right? This means what? In case of the tank is full, its natural period is higher than the case of the tank is empty, okay? And the value almost double. It is almost double of it, okay? This means that the system or the mass or this tank is going to take larger time if it's full in order to make one cycle. Okay. The second requirement, it is the damping ratio, which is psi. It equals to c over 2 the radical of k times m. Everything is known for us. This is again from the previous slides. I'm going to summarize everything at the end of this lecture so that it will be easier for you to remember. So damping ratio is going to equal C, the damping coefficient, over 2 times K times M. We know K, we know the M already, and C already from the previous example, we know it. Then we can obtain our damping ratio. So our damping ratio is 1.23%. However, the previous damping ratio, it was how much? Yes, 2.67%. What does it mean? It means when the mass of the system increases, the damping ratio is decreasing. And when the mass of the system is less, the damping ratio goes high. This means that there is a damping ratio relation with the mass, right? And this is true because we have here mass here, right? So this means that our mass is going to, so if we are saying that this damping ratio equal to C over 2 the square root of K times M, this means that there is a relation between the damping ratio and the mass. If we are going to decrease the mass, the damping ratio is going to increase, as the case in our example. Okay, it was 2.67% before when it was empty. However, that if we increase the mass, the damping ratio decreased. Okay, this is very important to remember and to know and to highlight this kind of relation. Okay, so that's important thing that I want to highlight here. That is important. Whenever that we have, like, we can put it like some notes here for you. So we can say that whenever the damping ratio is going down, okay, so this means that the mass is increasing, right? And whenever that CR, the critical damping ratio, is increased, is going up, the mass is going to increase as well, right? Because do you remember that CCR equal to what? 2m omega. So CCR and M, they are like proportional to one another. If CCR increase, the critical damping coefficient, if it increases, this means that the mass increases. Okay. And after that, if Tn is going to increase, then we're going to find that M is going to increase. Why? What is the reason? Because Tn equals to 2 pi over omega, which means that 2 pi times M over K. So M and Tn, they are proportional to one another here. However, here the damping ratio, the only equation that maybe I didn't put here, it is the damping ratio as we know, it equals to C over 2m omega. Okay, so this means that we have a relation between the damping ratio and M, okay, reciprocal. Okay, okay, so this is an important thing that I want you to remember. The last thing is related to some notifications, not modifications here, but we can say like important to remember. I'm going to put it like remember. Okay. Okay, remember this equation because I think they are going to be very important for you. I'm going to put it in like thick lines. So first of all, omega n, remember, omega n equal to the square root of K over M, okay, which equals to 2 pi over Tn. This is equation number 1. We call this the undamped circular frequency. Undamped circular frequency. Okay, this is number 1. After that, we have omega d, which equals to omega n times 1 minus psi squared. which equals to 2 pi over Td, the damped circular frequency. We call this damped, okay, circular frequency. Okay. And after that, we have something called the damping ratio, which is going to be C over CCR, which means that the damping coefficient over the critical damping coefficient. We call this the damping ratio, the damping ratio. Okay, it is very important to know. Okay, after that, we are going to have C, which is the damping coefficient. C equals to the damping ratio times CCR, the critical damping coefficient. We call this the damping coefficient. Okay. Oh, okay. So this is the damping coefficient. And then we have this CCR, which is the critical damping coefficient. It equals to 2 times Km, which equals to 2m omega. And this is the critical, we call this the critical damping coefficient. Okay? And then the last thing is the logarithmic decrement. The logarithmic decrement, which is equals to ln ui over ui plus n, which equals to n times 2 times pi times the damping ratio. And this is, we call it the logarithmic decrement. Logarithmic decrement. Okay, so this is things to remember. I hope that by the end of this class, you can remember all of these equations in front of you, because really they are important and you need to remember them almost in everything that you are going to do related to dynamics in general in your life. So the natural period here, the damped natural, the undamped circular frequency and the damped circular frequency, the damping ratio, the damping coefficient, the critical damping coefficient, okay, and then the logarithmic decrement. They are important to know and you need to remember them well. Thank you for listening to this video, and I hope that you could get more after studying and listening to it again. You can pause the video at any point and you can think and ponder over the equations. Sometimes I know that the rate of explanation a little bit fast, but I think that you can stop the video at any time and you can understand or you can ask me. Anyway, this is the end of this video. Thank you for listening and see you in the next video.